Here are solutions to homework set number 1 for ECE 376 for fall 2024. On this homework, we're just looking at some background on the PIC. Basically, what does 4.88 millivolts mean? That's the smallest voltage the analog input can read, the A to D converter can read. What does 100 nanoseconds mean? That's the smallest amount of time the PIC can read. So here are the solutions on the first page. I'll go over those in a little bit more detail. So the first problem asks, how many clocks does it take to do a floating point operation in C? Well, what this is getting at, if you go to Bison Academy, there are a bunch of different courses online. Go to 376, old homework sets and solutions. Here are the old solutions for previous semesters. If I look at spring 24, homework number 9, so here's spring 24, homework number 9, click on the solutions. So these are the solutions from last semester. It was using your PIC microprocessor. I can record times. How long it takes to do an integer add, that's 19.7 microseconds. How long does it take to do a floating point operation, 340 microseconds. How long it takes me to hit and release, RB0 10 times, 911 milliseconds. This is the one that I want. So it takes 340.9 microseconds to do this floating point operation. That's just kind of some advice. If you ever get stuck on the homework set, a good place to go are the old homework sets and solutions. Now the problems change every semester, but it kind of gives you an idea of how we approached the problem last semester. Probably pretty similar this semester. Problems do change, so don't just copy and paste, but we'll give you an idea of how to start. On problem 2, the PIC can only drive 25 milliamps. How large of a resistor can a PIC drive? Well, again, if we go back to, let's go to the end. This circuit, if I can only do 25 milliamps, and logic 1 is 5 volts, 5 volts over 25 milliamps is 200 ohms. So R3 has to be at least 200 ohms. What that means is that if this is an 8 ohm speaker, a PIC cannot drive an 8 ohm speaker directly. If you want to drive an 8 ohm speaker, you need to add 200 ohms to it so you don't get too much current. That reduces the volume. There are other solutions that we'll cover later, but you basically can't drive anything less than 200 ohms. Problem 3. This is the analog input. The A to D input on the PIC can read 0 to 5 volts with a resolution of 4.88 millivolts. What does that mean? So suppose I have a voltage divider. I've got two resistors. This is 500 ohms. This is 500 ohms. 5 volts. Nominally, I'll read 2.5 volts. Suppose this resistor changes. How much does this have to change for the voltage to change by 4.88 millivolts? Well, to do that, I'm going to increase the voltage by 4.88 millivolts. Go backwards and solve for R. Here's your R2. And you wind up that R2 has to be 501.96 ohms. So that's the resolution of the A to D converter in ohms. I can read 500 ohms with a resolution of 1.96 ohms. Problem 4. Suppose that resistor is a thermistor. That's a resistor that varies with temperature. How much does temperature have to change for the resistance to change by 1.98 ohms, for the voltage to change by 4.88 millivolts? So to do that, this is the relationship between resistance and temperature for the thermistor. At 500 ohms, solving for temperature is 41.6433 degrees Celsius. If, on the other hand, you are 501.96 ohms, meaning the voltage changed by 4.88 millivolts, solving for temperature is 41.5443 degrees Celsius, for a difference of 0.098. So that's the resolution of this as a temperature sensor. I can read temperature down to about 0.1 degrees Celsius. That's for the A to D converter. Next set of problems look at time. The PIC can measure time, 200 nanoseconds. That's a really, really small number. To give an idea how small that is, The world's fastest animal, the peregrine falcon, can fly 389 kilometers an hour. In 1 clock, it flies 10 microns. That is about 10 times the size of a bacteria, an 18th of the size of human hair. Is tiny. 100 nanoseconds is really, really small. If I have a 555 timer, this guy right here, if you have 500 ohms, 0.22 microfarads, what's the frequency of the square wave? Well, the period comes from this equation. Plugging in numbers, the period is 228.739 microseconds. Take the inverse of the period, it's 4371 hertz. So if I took that 555 timer, connect to a speaker, that's the frequency I would hear. Well, if the period changes, the PIC can detect that. So here I've got a square wave. This is the period. The smallest that PIC measure is 100 nanoseconds. So this gets longer by plus 100 nanoseconds. The PIC can see that. That's 1 clock. So the period goes from 228.739 microseconds to 228.839 microseconds, increased by 100 nanoseconds. Find the frequency. The difference in frequency is 1.9 hertz. The PIC can detect a change in frequency of 1.9 hertz at 4369 hertz. Suppose that resistor is a temperature sensor, a thermistor. What's the smallest resistance I can see? Change in resistance. So nominally it's 500 ohms, 0.22 microfarads. There's the period. If I make the period 100 nanoseconds longer, resolve for R2, that's what R2 has to be. That means with the 555 timer, I can now measure resistance down to 0.3 ohms. Now before it was about 1.9 ohms. A standard rule of thumb with computers are really good at measuring time. If you can convert your measurement to time, you can get a really insanely accurate measurement. Replace that resistor with a thermistor, 0.3 ohms becomes a change in temperature of 0.016 degrees Celsius. With this setup, I can measure temperature to 0.016 Celsius. And I can actually do better. I'm measuring the period of 1 cycle. If I measure the period of 1,000 cycles, I'll have 1,000 times the resolution, which is really, really impressive. So that is homework set number 1. Just kind of give you an idea that when we're dealing with the PIC processor, it's not the world's most powerful processor, but it is impressive. I can measure temperature down to 0.01 degrees Celsius. If I just measure one period, measure 1,000 periods, I have 0.01 millidegree C, 0.00001 degrees Celsius. I can measure frequency, very small changes in frequency. I can measure very small changes in resistance. So this is actually a very capable processor. And that is homework set number 1 for 376.